So, oil composition and weathering. We'll just get started. So I'm going to talk a little bit about oil. A lot of the folks in here, sounds like from your notes on the board there, probably know something about oil. Several of you work with industry, for instance. We'll talk about, for those of you who don't know much about oil, I want to kind of give you some basic primer stuff. It's been a long time since I've taken a chemistry class, but we'll muscle through it together. Just some differences between crude oils and refined oils, basics of oil composition, some of the key oil properties that are particularly relevant to oil spill response, and then we'll get into what happens to oil, sort of the fate of oil. Chris is going to talk later about where the oil moves and trajectory models, trajectory estimates. I'm going to talk about some of the weathering processes. Okay, so some of these slides are not my own, so we'll wrestle through it. This is a graph from National Academy of Sciences report from 2002 about oil sources to the oceans. There's a variety of different ones that are man-made sources. Most of these extraction, transportation, consumption, I think, is from non-point source pollution from stormwaters and such. But some people don't realize that natural seeps can be a dominant source of oil to the oceans. So it's not just people that cause oil spills. The environment has to deal with oil from lots of different sources. So I think it's an important thing to keep in mind, manage people's expectations, provide context, because it's not, it might help with some of the discussions. Oil is a very complicated mixture. It's a complex mixture of lots of different things, and we'll talk about this a little bit. It's naturally occurring. Once you know that, it can be either a gas, liquid, or a solid. It's a complex mixture of thousands of different types of compounds, mostly hydrocarbons. And it's used for all sorts of different things in daily life nowadays. It's not just used for fueling your car, powering your power plant. It's used for all sorts of things. Thousands of chemicals of different chemical structures, either straight chain hydrocarbons or cyclic hydrocarbons or aromatic structures. We'll talk about this very briefly, and they'll be touched on a little bit more as we go forward in discussions about environmental toxicology and so on and so forth. The oils are going to have, the compounds within oils are going to have different molecular weights, and that's going to affect how they're going to behave and their persistence in the environment. And they're going to have these mixtures of different compounds and different structures in different proportions depending on the oil. You have two general categories of oil: as crude oils, which are taken out of the ground, and then refined oils, or refined products, which are what come out of refineries. After crude oil comes in one end and refined products come out the other. And I'll talk about that briefly. But one thing to keep in mind about crude oils is there's I don't know how many hundreds, thousands of different crude oils across the world, and they all have different sort of chemical fingerprints, and they all behave a little bit differently. Some are sweet crudes, some are sour crudes, some are heavier crudes, some are lighter crudes, and that's all based on their chemical composition, and it's going to affect how they behave in the environment, how persistent they are, and how toxic they are, and what you might think to do, what you may have to do with it, and then those oils are going to be used to create different refined products. And it's done through a refining process, and essentially, I've never gotten like a in-depth tour of a refinery. I'd be interested in doing sometime, but basically what they're doing with the crude oil is they're heating up the crude oil to different temperatures, and at the lower temperatures, the more volatile components of the crude oil come off, and they're going to create things like gasoline and other lighter weight refined products. And then once those have kind of already evaporated off, then they crank up the heat a little bit more, and then some of your heavier products start coming off, and that's more like your diesels, your kerosenes. And as you continue through that process, it's going to take more and more heat to volatilize off these heavier compounds, and so you're going to have lighter compounds coming off first, lower molecular weight compounds, and then as you go through, you're going to have much heavier, more viscous types of oils at the end. So it's sort of like a sequential fractional distillation is what they call it, where they're separating things essentially by their boiling points, different fractions of that crude oil. And as you go through that fractional distillation process, boiling temperatures increase and the viscosity of the stuff still in the tank is increasing too, because the lighter weight stuff is being boiled off. And so the differences in molecular weights of those types of refined products like gasoline versus diesel versus intermediate fuel oil are going to be different, partially because just the molecular weights of those compounds are different. Gasoline is going to evaporate more easily, so it's not going to persist as long. There's going to be heavier compounds in a heavier fuel oil. It's going to have potentially different toxic effects. It's going to have a different duration of persistence and those sorts of things. So it's helpful to kind of at least understand and appreciate how the complexity of the oils and the refined products is going to affect how it's going to behave in the environment. Does that make sense? So, as I said before, oil is used in all sorts of different things, common products that we use every day. People don't necessarily think about that a lot. I'm not going to spend any time on this. Just realize that there's a lot of stuff out there that are dependent on the crude and refined products. I'm also not going to talk about fingerprinting because we've got a person from one of their OSPR labs going to talk about fingerprinting. But one thing I do want to point out is that it's that complex mixture that allows fingerprinting to occur. So that's about all I'm going to say about that. And we're going to have a discussion about that later on today. It's also that complexity and the different grades of oil that are going to determine whether people call it light oils, light refined products, or heavy refined products. Typically, the lighter refined products are going to be less persistent in the environment than heavier products, and typically they're going to have a higher acute toxicity than the heavier products. It's going to depend kind of on what the chemical mixture is of a particular refined product. But generally speaking, that's how it's thought of. Gasoline is typically going to be less persistent than IFO. But it's that chemical complexity that is going to affect an oil's toxicity, persistence, and behavior in the environment. These are pictures from Deepwater Horizon. Relatively fresh oil near the source, and then tar balls on the shoreline. Same oil, but very different character because it's weathered over time, and we'll talk about weathering as we go forward. It's also going to affect how the oil behaves on the water, how it interacts with the water. Chris may talk a little bit about, how oil movement may change over time because of the way it weathers, and how it interacts with shorelines. And we'll talk about that a little bit too. So this is not my slide, and I actually have never seen. This is a slide from one of our response chemists up in Seattle. I think the question is something like, what's the difference between oil and a frozen turkey, freeze-dried turkey? And because I've never actually seen him give that talk, I'm not even sure what his answer is. My guess is, chemically, it's not very different. I think, chemically, elementally, it's not very different. I think it's probably the structure of those elements and the molecular structures that are involved. And so that help distinguish oil from a freeze-dried turkey. Is that kind of, sort of?
One tastes a lot better.
Is that plausible explanation anyway? I'm sorry, was there a comment?
So one tastes better.
Yeah. I won't ask you which one. I don't want to get, your family members in trouble with Christmas or Thanksgiving. So I'm not going to get into the structures because when I took organic chemistry and my eyes tend to glaze over when I see these structures. And I'm not a chemist. I appreciate the value of chemistry and chemists and those technical specialties, but I'm not going to be drawn molecular structures for the commander on any spill upcoming. But a bulk of what oil is composed of is what are called alkanes or cycloalkanes and aromatics, and we're going to focus on those for the next couple slides. Alkanes are saturated hydrocarbons. They can come in straight chain hydrocarbons like this, or like this. Sometimes you'll have a functional group kind of jutting off to the side, or they can be cycloalkanes, which are just a circular structure. They'll have different names depending on how many carbons they have in their structure. These are all single bonded carbons, which helps distinguish them from the next category we'll talk about. And they can make up a substantial proportion of an oil mixture. One of the things about alkanes and cycloalkanes is because of the nature of their structure, they are more easily broken down. They're more easily degraded in the environment. Biodegradation is simpler for microbes, for alkanes, than they are for aromatics, which we'll talk about in a little bit. So their half-life is generally going to be shorter in the environment than an aromatic compound. Aromatic compounds are very similar, except they'll have an alternating double bond in these. They'll be cyclical structures, but they'll have alternating double bonds and single bonds as opposed to the alkanes, which just, I don't have a picture, which are all just single bonds. And that makes them, gives them different properties. An aromatic hydrocarbon is one that contains at least one of these types of structures in it. There might be multiple rings that are fused together, but it's going to have at least one benzene ring in it. It too can, aromatic hydrocarbons can also make up a substantial amount of the oil volume. And aromatic hydrocarbons is oftentimes what is associated with different types of toxicity associated with oils. So when we talk about aromatic hydrocarbons, we talk about VTEXs or VOCs, those lighter end products, which are typically one benzene ring with a different functional group on it. Or you'll talk about polycyclic aromatic hydrocarbons like benzoylpyrene, where you have a bunch of different rings stuck together. And the VTEX compounds with a single benzene ring, those are often associated with acute toxicity. You know, a relatively quick hard hit to a critter, for instance. Polycyclic aromatic hydrocarbons are oftentimes thought of as more of a, they're more persistent in the environment, they're going to tend to be more associated with chronic toxicity, so like cancers and tumor growth and things like that. But I don't want to get into too much of that because we have ecotoxicology studies coming on later. And also, Becky might talk about it in terms of NERDA. So just to kind of give you an idea that there's kind of different classes of compounds that we think about when we're talking about response chemistry or oil chemistry. There's also another group of compounds in oil mixtures which are thought of as polar compounds because they contain either nitrogen, sulfur, or oxygen, and they're often going to be in higher proportions in your more viscous, denser oils, and they may be one of the reasons why we have certain oils behaving certain ways in the environment, and I'll touch on that in a little bit. So, typical composition of these different refined products. We talked about how the lighter weight refined products like gasoline tend to be lighter, smaller molecules, lower molecular weight. They'll tend to have between 4 and 12 carbon atoms in their mixture, sort of that range. Kerosene and diesel are going to be fairly similar, and intermediate fuel oils. You know, it's going to be a heavier oil, but sometimes in the marine industry, it's blended with a lower, like some sort of cutting element to kind of thin it out for purposes of using machinery. But they're all going to behave a little bit differently. They're going to have different properties. For the purpose of spill response, I'm going to focus. There's a whole list of different physical properties that can be used to describe oil. I'm going to just focus on these three primarily, starting with density. So there's density, or for you David Letterman fans, will it float? I should have had it twirl and make noise, but I don't know how to do that in PowerPoint. So density is mass per unit volume. Oftentimes when you think in chemistry about density, you're talking about specific gravity, which is how a given volume of a compound relates to its same volume, the same volume of water, fresh water. And so a specific gravity of an item is less than 1, then it will float in water. When you're talking about oils, the U.S. petroleum industry uses a different measure or a different way of describing density of oils, and that's by using API gravity, which many of you may be familiar with. But you don't really need to know this equation, except the thing to appreciate about it is that it's an inverse to specific gravity. So anything that is less than 1 specific gravity is going to float. When you get to API gravities, it's anything above 10 will float. So it takes a little while to get used to that difference, but recognize that that there's a difference in how specific gravity expresses density and API gravity expresses density. Does that make sense?
We need to know what API is.
Sorry?
For those of us that are not like chemically inclined, does APA stand for something that?
American Petroleum Institute. I'm not sure
Okay.
I'm not sure the background of that equation and who developed it and why it's an inverse relationship and why they use that and not specific gravity.
Yeah, it's an industry standard. They used it, American Petroleum Institute, they used it as a standard so they could talk across the industry. And so in the industry that we all kind of know and use it, we also use.
So oftentimes in spills, when you're talking about a hazmat spill, you're usually talking about specific gravity. When you're talking about oil, you're usually talking about APIs. So we're talking about, just to kind of give you a little comparison. So fresh water, like I said, is going to have a specific gravity of 1. It's going to have an API gravity of 10. And if you put fresh water in salt water is denser, so fresh water is going to float on top, right? Salt water, as I said, is denser than fresh water, so it's going to have a higher number for specific gravity and a lower number for API gravity. And obviously, if you put salt water in salt water, it's not going to either float nor sink, it's going to mix. Most oils are floating oils, so they're going to sit on top of the water. So if you think about an oil in terms of specific gravity, you're talking about ranges like this. They're typically less than 1. When you're talking about API gravities, which is how you normally describe the density of oils, you're talking about something generally in the range of between 10 and 50. And so they're going to float in salt water and fresh water. This is an example of a sinking oil incident that happened off Port Arthur, Texas in November of 2005 as a result of some hurricane damage from Katrina and Rita. This integrated tank barge was carrying a heavy fuel, which a bulk of their cargo was well below 10 API of 10. So you'd have the spill, you'd have the hole in the ship. There'd be oil on the surface, and you're standing back and looking at it. The salvage guys are saying, oh well, it's still stable, it's still upright, and there's not much oil on the surface, so things look pretty stable. But over several days, it turned turtle, and they realized that it had lost a lot more oil than they had originally anticipated. And part of that's because it was a really heavy oil, and it never showed up on the surface because it went straight to the bottom. So what they did was they grabbed some samples. Some of the coasties went out there, strike team folks, went out there and grabbed some oil samples and filled up an aquarium in the command post of the seawater from out of the site, and they squirted in there and see what happened, and it went straight to the bottom. And this is a diver video screenshot of the oil just kind of sitting on the bottom. If you watch some of the videos from this incident, diver videos, they'll come across a puddle of oil in the water. It's not only was it a really dense oil, but it's a low viscosity. So they waved their hand over the top of it, and it would break up in these little droplets and just mix all that. It's kind of cool, but challenging from a response standpoint. And this is just an example of different California oils, either in platforms or that are near the coast. So, but they're all above API of 10, so they're all floaters, but some of them are kind of close to 10. So it may affect how much wind is going to be a factor in its movement. It may affect other things too. So another thing about API gravity, and I said there's a figure in the back of this talk about oil groups. A lot of Coast Guard regulations talk about oil in terms of group numbers, groups 1 through 5. Those are all defined by the API gravity of oil. So oils between API of whatever and whatever are group 3, for instance. And there's a figure in the back that kind of talks about that a little bit. I'm not going to get into it any more than that, but just recognize that some of the Coast Guard regulations are based on group numbers, which is in turn based on API gravity. And so you may hear that terminology. Group 5 oil is a sinking oil, for instance. So that DBL 152 spill, that was a group 5 oil. Just something to recognize. Viscosity. This is whether or not how much of a liquid it is, how pourable a liquid is. It's a measure of the fluid's resistance to flow or spread. It's temperature dependent, so obviously if you have a jar of honey in your refrigerator, it's going to be pretty thick and slow to pour, but if you heat it up a little bit, you know, to 75, 80 degrees, it's going to pour much more easily. That's the temperature effects on the honey's viscosity. As an oil weathers and it loses a lot of its lighter end compounds, its viscosity is going to tend to increase over time. This viscosity is going to affect an oil's tendency to spread across the surface of the water. So if I had, let's say, water in a bottle and poured it on a concrete floor, it's going to spread out pretty quickly and pretty far because it's low viscosity. If I had a bottle of honey or peanut butter, it may not spread out very far at all or very quickly because the viscosity is higher. It's also going to affect physical dispersion and emulsification. We'll talk about those properties in a little bit. Depending on the type of shoreline, viscosity may affect how deeply into the shoreline substrate that oil penetrates. If you have a coarse-grained sand, a lower viscosity oil is going to be able to sink deeper into that sand than a high viscosity oil. And also viscosity may potentially affect the types of tactics or equipment that response might need. So a real high viscosity oil will burn out a lot of pumps unless you have to pick the right pumps that are designed for the purpose of pumping low viscosity oils. So it's something to keep in mind. But viscosity, this is a list of some common items and their relative viscosities, which makes sense when you think about it. Water is far less viscous than peanut butter. No big newsflash there for you guys, I'm sure. And viscosity, like I said, can make one spill very different from another. This is from the Salindang IU spill. It's an IFO 380. Not a highly viscous oil, but when you put it into a cobble boulder shoreline, it can penetrate pretty deeply, and that can be from a cleanup standpoint, might require a certain set of tools and might be kind of a headache. In this case, this particular shoreline segment was quite a big headache. Or if you have more viscous oil on a different type of shoreline, it may also make a mess, but it may have vastly different response tactics used and might be much more easily cleaned up, just by virtue of the shoreline and the viscosity of the oil. So it can be an important consideration in oil spill response. Pour point, this is a temperature, so it's usually given in a temperature above which oil will flow. It's certainly related to viscosity, but it's really the temperature that the oil will flow. It's kind of a subjective measurement, so the information that might be in the MSDS or in your oil chemistry information may not be exactly what you would see in the field, but I see it as kind of a guideline for responders. If the ambient temperature of an area is 80 degrees and the pour point of the oil is 45 degrees, then you would likely see it as a liquid, because the ambient temperature is above the pour point. Similarly, if the ambient temperature is well below the pour point, it may be relatively solid. So there was a Westchester spill in Mississippi River. I think the pour point of this oil was 45 degrees. At night it would get below 45 degrees, so it would be relatively solid, but during the day it would heat up and turn to liquid, and there would be a much different response scenario. Similarly, for the Morris J. Berman spill of Puerto Rico in '94, I think it was, you had this floating oil that came in, picked up a lot of sand on the beach, and then sank near shore. But then in the afternoon, in the shallow water, as the sun would heat up the oil, reduce the viscosity, and those sand grains would drop out of the oil would float up to the surface again. And so you'd have a very different surface expression of this oil during the warm daytime than you would at night. So it's something potentially important in a spill response. Flash point is another potential consideration, particularly for responder safety. This is also described as a temperature itself. The temperature at which vapors can explode or ignite. This is another physical property of an oil that will change as the oil weathers. You have the lighter end products evaporating off, and so as an oil gets older or more weathered, its flash point is going to increase. It's going to take a higher temperature to ignite that oil. Certainly, It's a consideration in situ burning, and Ellen Daniels is going to talk about in situ burning later on this week when she talks about applied response technologies. It's also certainly a potential consideration for responder safety, as many of you guys know. I don't know this incident specifically, but it was Flashpoint was a consideration because this incident turned into a much different situation when stuff ignited. So it's potentially important. So just to kind of get back to the different sort of groups of oils or grouping categories of oils, you have gasoline, which is a relatively low molecular weight refined product. It's going to have a low flash point, low viscosity, right? It's ignitable at lower temperatures, and it pours really easy. Diesel is similar, except it's going to tend to have a higher flash point, but it's also going to have a lower viscosity, so it may be able to penetrate porous shorelines relatively easily, like gasoline. When you talk about intermediate fuel oils, it's going to tend to have a higher flash point and a higher viscosity, so it's going to present different response issues to deal with than the lighter refined product. Does that make sense? You guys still hear me in the back? I don't know if I'm getting quieter as I go along. So, quiz time. As the temperature decreases, does the viscosity decrease or increase? I heard it once here. Increase? There you go. Wow. It's not rocket science, it's just chemistry. Would you expect an oil and API gravity of 25 to float or sink in fresh water? You guys are cheating. You're just reading it in the book. No, Coast Guard would never do that. Okay, so I'm done with the physical properties. I'm going to talk about oil weather. And I've got, well, I guess I have a half an hour, but I'll try to keep this short. So when oil gets spilled in the water, depending on its chemical composition, it's going to first spread. That's one of the initial things that happens. And it's going to weather through several mechanisms which I'll talk about. And then it's going to be transported by winds and currents, which Chris will talk about after lunch. So spreading, as I said, is dependent on the oil's viscosity and the local temperature. And it's, like I said, if you poured honey or olive oil on a concrete floor, it's going to spread out at a certain speed and a certain distance because of the nature of its viscosity. It's also going to be weathering and moving across the oil surface, but spreading is an activity. It's a process that happens relatively early when the oil hits the water. So oil hits the water, it's spreading out, but it's also moving and weathering at the same time as it moves downwind and the current. But it's that spreading part which I'm going to touch on first. So when an oil is, like a black oil for instance, is released to the water, oftentimes it's released into a continuous slick, and it's going to continue to spread out and get thinner and thinner, and the waves are going to break it up, and turbulence is going to cause it to break up into smaller and smaller pieces. It's going to turn into streamers and maybe become more patchy in its distribution. The thicker black oil is going to get thinner and thinner and going to be seen as sheens, like a rainbow sheen or a silver sheen. That represents a thinner layer of oil as it gets more spread out over the surface. As I said, it's initially driven by the oil's viscosity and, of course, gravity, which isn't going to be varying too much across the open ocean. It can make a relatively localized spill into a big deal. It doesn't take much gasoline or diesel to cover, if you have a spill in the parking lot on a wet day, you can see rainbow sheen all over the place. It doesn't really take much oil to be visually conspicuous. And a lot has to do with spreading. It's controlled by oil type, the volume of the oil is released, so on and so forth. It's usually something which we think about in terms of spill response in the first few hours. And over time, it's going to break up. The slick is going to break up. So I think that's all I want to say about that. Weathering is a variety of different processes that gets you from fresh oil to something that's more weathered, like tars and asphalt, things like that. There's those two-sided fact sheets in the back of this presentation in your handbook. Talk about the weathering of different types of oil, like small diesel spills or Alaska North Slope crude. And this figure is from one of those fact sheets. as an oil weathers, it tends to get from more flammable to less flammable because those lighter end compounds are evaporating. Its viscosity tends to increase, so it tends to turn from more of a liquid state to more of a solid state. It's not as smelly over time because those lighter ends have already gone away as it evaporates. And because acute toxicity is typically associated with the lighter ends, the BTEXs or your VOCs of volatile organic compounds, the acute toxicity tends to decrease over time. Though the residual heavier compounds may continue to cause a persistent chronic toxicity issue, but that's, I think Becky may talk about acute and chronic toxicity later on. The different oil weathering mechanisms kind of have their own different time frames. Typically, when you're talking about oil, evaporation and physical dispersion are usually relatively quick in a matter of hours to maybe a day or so. Some of these other processes, like emulsification and sedimentation, it takes is kind of a little bit later on in a spill incident. Biodegradation is a relatively long-term weathering process, and I think Kathleen talks about that later on this week when she talks about bioremediation project and stuff. So they all have the different time frames and maybe different primary loss mechanisms of oil over time. This is a screenshot from one of our oil weathering models called Audios, which is available on our website. You can download and play with it all you want. This is just showing evaporation, an oil budget figure of evaporation. Evaporation is particularly for lighter fuels and lighter oils. It's going to tend to be one of the major loss mechanisms of a surface lick, because those light ends, if an oil has a lot of light end compounds, they're going to evaporate more easily, and so you can potentially lose a high volume of your initially spilled oil just from evaporation alone, depending on what the wind conditions are in the oil and so on and so forth. Just because you're losing lighter end compounds doesn't mean that the density of that oil changes significantly. It might change a little bit, but it's not going to. I think in the 35 years or so that our folks have been doing oil spills, I don't know if we've ever come across a situation where, as an oil weathers, it became from a floating oil to a sinking oil without some other thing causing it to sink, like sand or debris or something like that. But theoretically, it can have an impact on density. It can have an impact on viscosity, though. But I don't have an example of that. So, like I said, gasoline evaporates pretty quickly. No big surprise there, but it's interesting to kind of see the differences here. It's kind of talked about in those fact sheets a little bit. Crude oil, because it's a crude oil and has both light ends and heavier ends, you can lose a pretty substantial amount of a crude oil just from evaporation alone, because it's, like Alaska North Slope crude, you might lose 20-25% in the first 24 hours just because it's got a lot of those light ends in it. Louisiana crude you might lose more from evaporation because it has a higher proportion of lighter ends in it, for instance. Some of your heavier fuels, you may lose some, but not nearly as much, and it will take much longer. So, for instance, this, it doesn't take much for gasoline to evaporate. It may be that if there's a gasoline spill, you may not even bother to launch a response because it may be gone before you get there.
So when it evaporates, when it evaporates, is it breaking down in the atmosphere?
It will photooxidize over time, but it's certainly going to dilute quite a bit. So the toxic concern would be, potential toxic concern would be greatly reduced. And the oil wildlife care folks might talk about inhalation exposure to wildlife. Yes, Josh?
I would say that the toxic impacts might be reduced, but not locally while it's happening, right? You might have an issue
Right at the surface of the oil, there's still going to be relatively high concentrations of air, but it wouldn't have to go very far to get drastically lower concentrations of toxic compounds in the air from the oil spill. Right. So the first one was gasoline. Almost all evaporated like within an hour. Louisiana crude, like I said, a good proportion of it in this case, like, 25, 30% of it evaporates relatively quickly. An IFO, much lower percentage. So if you had a 1,000-barrel spill of gasoline, it may be gone in hours, but a 1,000-barrel spill of IFO, you may have a lot to deal with, just days down the road. Physical dispersion is another mechanism to remove oil from the surface, water surface. It's the turbulence. It's going to be dependent on the oil, viscosity of the oil, the temperature, ambient temperature and pour point, and certainly the turbulence, so the wave energy in the area. It's basically breaking up. That turbulence is breaking up the slick into little tiny droplets and pushing those into the water column. Larger droplets are going to have a higher rise velocity, and so they have the potential of resurfacing and recoalescing into a slick again. If the droplets are small enough, then their rise velocity is not high enough to overcome the ambient turbulence of the area. So though it may still be a floating oil, it might be such a small droplet that it would take days for it to get back to the surface. And because there's going to be inherent turbulence in the surface waters, you may never see that droplet come up to the surface again, in theory, just because of the nature of the physics of it. So that's putting little droplets of oil into the water. This is an example of a spill off New England where I think it was a diesel or number 2 heating fuel. So it's a low viscosity oil. I think it was a grounded barge. It happened in the wintertime, winter storm, near shore, crashing surf, big storm. Basically pushed all that diesel or number 2 heating fuel from the surface into the water column and killed off huge amounts of clams and lobsters and shellfish. So there was no oil that really reached the shoreline, but all these dead animals started washing up. So there really wasn't a lot you could do from a response standpoint. But I suspect there was a big natural resource damage claim on that one, just because of the nature of the oil and conditions. Another figure demonstrating physical dispersion of oil. On Deepwater Horizon, there's a lot of stuff in the news. You saw about kind of what that day's footprint of the oil was based on satellite imagery. Well, I don't know if this is the FOSC report or where this figure came from, but this is a graph of, if you look at the blue bars, that's the square kilometer area of the slick footprint based on, I believe, satellite imagery. And the red line is the wind overlaid at the same time. So you can see how when the wind was at relatively low levels, all those little droplets of oil were able to rise to the surface because the surface was less turbulent. And so it looked like a bigger spill because there was less turbulence, so you had a larger area of sheen and different types of oil expression. And that's largely because you didn't have as high a turbulence in those low wind conditions, so you had less physical dispersion of that oil into the water column. Does that make sense? Kind of a busy graphic, but it's colorful, so I like it. Dissolution, or the dissolving of oil compounds into the water. That's closely related to dispersion. The more physical dispersion you have of oil into the water column, the more likely it is that some of those compounds are going to dissolve into the water column as well. So that was probably part of the reason why all those shellfish were impacted during that North Cape spill. Yes, sir?
Just a quick question about the dispersion and the shellfish example that you gave. It seems as if you need to mop all that up too because of the food web.
You would, as a responder, you might be potentially concerned about scavengers and secondary contamination. I don't know if I wasn't on that spill, so I don't know. I suspect that they were carted off, so you don't have scavengers eating it. I know it can be a potential issue. I know on the Selendang IU spill, there was a big concern about secondary impacts to scavengers, and so anytime anyone, even scat teams, came across an oiled bird carcass, they would pick it up, if for no other reason than to minimize impacts of bald eagles and foxes and things. But it could be a potential consideration. But you may not, so you're picking up contaminated stuff, not necessarily shoreline oil.
Yeah.
So it might be a relatively short-lived response overall. Typically, the types of compounds from oil that are going to tend to dissolve are your lighter weight compounds, and they can oftentimes have a acute toxicity. Higher proportion of gasoline is going to typically can have the potential to dissolve in the water column than heavier oils. But not much overall. So this is an example from Deepwater Horizon of both dispersed and dissolved compounds. If you're not used to looking at these graphics, it's a little bit difficult to understand. Or it takes a while to get used to it, I guess. This is depth in meters. So if you remember hearing about the plume of oil down the deep sea plume of oil at about 1,200 meters, this is a reflection of that. This black line is an indication of oil levels based on fluorometry. I think we might touch on fluorometry briefly later. So at about 1,200 meters, there's this layer of oil droplets and dissolved hydrocarbons, and this red line is the dissolved oxygen concentration as you move down from the surface down to 13, 14, 1,500 meters. And so what's happening here, or the inference you can take from this, is that microbes are starting to eat the oil and that subsurface plume, and that's they're using up oxygen as they're consuming those oil droplets and the dissolved components, and so it's causing a decrease in the oxygen concentration. But it never decreased oxygen concentration low enough to cause the water to become hypoxic and be a threat to other organisms in the area. So anyway, it's yet another example of dispersed oil and what the potential impacts could be and considerations during response. Emulsification is another weathering mechanism. When we talk about physical dispersion, we were talking about putting small droplets of oil into the water. Emulsification is kind of the reverse of that, where you're putting small droplets of water into the oil. You're turning it into what people call sometimes a mousse. You're basically whipping, based on the turbulence and the type of oil and how weathered it is, you're forcing water into the oil and making it more viscous, and you can increase the volume of that oil stuff to a much higher degree than the initial spilled volume. So there are times when some emulsions can be up to 70 to 90% water. I think the emulsification process is not really well known. It tends to happen with more weathered oils. I think it tends to happen with oils that have a higher proportion of polar compounds, those nitrogen, sulfur, and oxygen compounds that I talked about earlier. And the resulting emulsion is typically more viscous and sometimes more persistent than the apparent oil. So like you think of for, mayonnaise is a type of an emulsion. It's much more viscous than either the oil that you're using, like olive oil or vegetable oil, or the egg that it was used to make. So it's more viscous, and the volume of it is much larger than the parent compounds. Does that make sense? Another thing about emulsified oil is it can oftentimes change the color pretty drastically. So a lot of times, like in Deepwater Horizon, and this may be a Deepwater picture, I'm not sure. The brighter the color, the more emulsified the oil is. So like here, this darker oil here might be less emulsified than this orange. This brown has some higher content of water, a little bit more emulsified, and this bright yellow is a highly emulsified oil. And that emulsified oil may have a certain amount of stability. It may last for a while, or it may not, depending on the temperatures and the properties of the oils are. But it can be kind of, sludgy, highly viscous, kind of larger volume when you look at it up close. This is from an overflight. Different degrees of emulsification of Deepwater Horizon oil. I don't know if this is in a skimmer tank or just where, but it's emulsified oil. Sedimentation is another loss mechanism of surface oil, another weathering mechanism. Like I said, most oils float on the surface, but sometimes if sediment gets stuck to oil or debris, it can cause it to sink. And that would be thought of as a process of sedimentation. So either in a really muddy river like the Mississippi River, you may have a surface slick that disappears over time as it moves downstream, and part of that's because the sediment is scouring the underside of that oil and causing little bits of it to drop off and sink. Or you can have, like I said before, a floating oil that comes into a shoreline, a beach, picks up sand, and that sand is enough to cause that oil, that floating oil, what normally would be a floating oil, to sink, and that's just a sedimentation process. Biodegradation is another process, weathering process that can occur to oils, but that's a much more longer-term process. That's where microbes kind of eat up the oil. As I said, alkanes, those simple hydrocarbons are going to be broken down more easily, so compounds that have more aromatic structures in them are going to tend to be more persistent. But those oil degrading bacteria are all over the place. They may not normally be exposed to oil, but you will see a change in the microbial community in an area of an oil spill because of the input of oil. Gulf of Mexico, there's a lot of natural seeps there, and microbes are pretty well attuned to breaking down that oil. If they weren't, then the entire shoreline of the northern Gulf of Mexico would have been paved millennia ago, because there's so much natural seep oil that goes into that area. But it took a lot of explaining to the general public to make them realize that microbes could potentially be a significant loss mechanism for oil from the deep water horizon. Which is why this is here. So as an oil spreads out, breaks up, weathers, its oil character is going to change. It's going to move from a slick to streamers to tar balls, and those tar balls are going to be particularly persistent over time. And they're going to be difficult to track from the air. You probably can't see it in this lighting, but you can see little flecks of oil here on the surface. And I think this is from, I don't know if this, I think this might even be from a boat or a low altitude helicopter or something. I'm thinking it's a boat because there's no rotor wash in the water. So it's really hard to see these little black dots here. Anyway, so you can have oil from an oil spill showing up quite a ways downstream, but it may show up in the form of tar balls, which may be another different type of response consideration. And tar balls can be pretty persistent in the environment. They may, the outside layer of a tar ball may weather, and the inside might stay relatively fresh sometimes. They'll wash up on shore, and then they'll bake in the sunshine, and so they might heat up enough so that they start to flow a little bit, and they might penetrate into shorelines. So it's something to think about over time.
Question.
Yes.
Is there any actions that can or should be taken when you see tar balls? I mean, I know tar, I guess not tar, but oil kind of seeps naturally, so I guess they can create tar balls. And you're saying that these things can also kind of travel into miles, and so they can probably also last after oil spills occurred long ago. What can be taken? I know that there was also mention about, DNA type things. So from my perspective, I guess again, from a coastline operator,
Sure.
if I see this stuff happening, is there something I should be doing?
Well, there's a couple thoughts that come to mind with this question. One is that sometimes you get natural seep oil that washes up from Southern California and comes up on your shorelines. And Coast Guard can talk about whether or not, what type, whether they would respond to tar balls from natural seep oil or not. Oftentimes that becomes a question, particularly in the wintertime, whether or not that seep oil or the tar balls that showed up on a beach in San Mateo County is from an oil spill or from natural seeps. And so there's oftentimes like a flurry of activity to get some samples into the petroleum chemistry lab and look at the wind conditions recently and the current conditions and try to determine whether it's natural seep oil or from an actual incident. If it's an actual incident, the Coast Guard is going to be all over it because there's a potentially responsible party out there. There's laws that have been broken, so on and so forth. And that's a whole different situation than if it was natural seep oil. It's typically difficult to go out and just kind of scoop up tar balls off the water. And those tar balls may not actually present a risk to wildlife, because, particularly if they're not tacky or sticky anymore. So it may be that if you're going to pick it up, it may be that the easiest option is to wait for it to come to shore and then pick it up, or something like that. rather than sending out an armada of vessels to try to pick up these little bits of oil in place. Does that kind of get?
Yeah, but, you know, for us, it's like a public concern, because, I mean, as the public starts hearing more about spills, and they become more heightened and concerned about it, if they go out and all of a sudden they're stepping in off the shore, and then they've got stuff sticking on their feet, because they go into a lawn and they want somebody to take action like immediately, and so.
Right,
that's
so-
not what we do.
Well, part of it's managing people's expectations to some extent, and making them realize that some of this stuff is natural and it's not, and so it's treated differently from response agencies than an actual vessel spill. Southern California, the shorelines, recreational beach users in Santa Barbara Channel encounter tar balls quite a bit, and so they're kind of used to it. They, a lot of hotels have little cleanup stations at their pool decks. You clean the oil off your feet before you get in the pool or something. In Northern California, not so used to it, but maybe it's reasonable for those coastal counties to at least be aware of that, and maybe if it's a natural sea oil and people are concerned about it, and it's not something that response agencies are going to go out and deal with, maybe that's an option to help kind of keep the public a little bit on that. So a lot of these weathering mechanisms are, you can kind of get a better, build your intuition by using our oil weathering model, ADIOS model, which I won't demonstrate, but it's available on our website. You can download it, you can play with it. It's not authorized for Coast Guard standard workstations, but anyone else can use it. Sorry, guys. And you can kind of get it'll help, like I said, it'll help you build that intuition about, how much wind might affect different types of oil in an open water spill scenario. And this is oftentimes what we'll use or what folks will use in either a drill or a spill when they're filling out their ICS 209 oil budget fields. They'll play with ADIOS and they'll come up with at least some estimates to put in these boxes. So rules of thumb. Higher API oils, the ones that are, lighter, they're less dense, they're going to float higher. Things like gasoline, they're lower molecular weight compounds, so they're going to tend to be less persistent. They're going to tend to have a higher acute toxicity. They're going to be less viscous, so they're going to spread out more quickly and further. Medium weight oils are going to be a mixture oftentimes. They may have a acutely toxic component, but they may also be persistent enough to cause a smothering impact potentially. Low API oils are going to be thick, heavy, black, viscous kind of stuff. You may see them form into tar balls. They may not have as much of an acute toxicity issue. They might be more of a smothering impact or a long-term chronic exposure impact. And they're going to be stickier, so they may be more likely to pick up sand, for instance, and sink offshore. So the whole concept of oil composition and the complexity of the mixture and the weathering is what causes a relatively fresh oil, a shiny, iridescent, low viscosity black oil, into something that's a little bit stickier, tackier, a little duller in color, more viscous, to something that might be almost not sticky at all. It's almost almost looks like dry paint on rocks. But it's that chemical complexity and understanding and appreciating that complexity of that mixture that might help you understand the kind of weathering process a little bit.